Thank you. So first of all, I would like to say that it's a great pleasure and an honor to be able to give this talk on this conference celebrating the 90th birthday of Maurício Peixoto. So I'm going to talk about a charge. Well, it's a 2-degree of freedom Hamiltonian system of a charge moving on an electric lattice of fixed particles. So you can think of it as, in some sense, of a crystal with some fixed ions, and you can think of, and we will look at the motion of electrons moving through the lattice of the crystal. Okay, so the talk is structured as follows. First, I'll give a brief description for the problem and some ideas about some previous works around this subject. Then I'll formulate the problem precisely. Then I'll describe the interaction between the energy level sets and the interaction potentials, describing the interaction between the moving charge and the fixed particles on the lattice. And then I'll prove that there is chaotic motion. By that I mean that there exists an invariant set on some energy level set, which is a suspension of a subshift of finite type with positive topological entropy. In particular, this ensures that the system is not integrable. That is, apart from the Hamiltonian, we won't be able to find another first integral. Okay. Okay, so the main ingredients are the following. So I'll consider a lattice in R2. So I'll pick R2, and then the lattice Z2. I can do this for any for any lattice generated by two linear independent vectors in R2, but let's just stick with a quadrangular lattice. Okay, so we fix this lattice, and we assume that all points in the lattice are charges with some positive mass, and for instance, let's fix the mass and charge equal to 1. So choosing units of mass and charge so that these are equal to 1. So now we look at the motion of another charged particle, which can be either of the same signs of the fixed charges or opposite signs. So now we also have an extra ingredient. We have a magnetic field which is orthogonal to the plane of motion. Again, let's just stick to this magnetic field. We can also have an electric field. But let's make the electric field 0 and just focus on the magnetic field. So the charge, moving charge, will feel the force, the Lorentz force induced by the magnetic field, which makes it turn around. And it will feel also the attraction by all the particles in the lattice. Okay. So the idea, apart from the one that studying the motion of this charge moving in a sort of a crystal, the other idea is that this can also be seen as the dynamics of one free particle moving in a torus under the action of a magnetic field, which is orthogonal to the torus, and a fixed center on the torus. But now each one of these lines connecting the fixed part on the lattice will be generating, in some sense, a direction in the tori. So the particle, the moving particle, will fill this particle in an infinite, well, countably infinite number of ways. Okay, so this would be, in some sense, an example of a charge in a magnetic field in a curved surface. Okay, so the goal of this talk is to give some idea about the dynamics of this Hamiltonian system. Okay, so I should tell that there is already an old paper, well, Backnoff in 1987, in which he studies the motion of one particle, which is in basically this setup, but with no magnetic field. So the particle feels negative Coulombic forces, so attractive Coulombic forces by each one of the particles in the lattice. So in our case, we consider both the attractive and repulsive case. And we have the magnetic field. So it proves that this flow is Anosov for sufficiently large energies and ergodic, and moreover, it proves that the flow is diffusive in a measured theoretic sense. So its construction is the following. It moves from the Euclidean metric to the Jacobi metric. So basically, it introduces a new metric, G prime, which is H minus Vx G, where G is the Euclidean metric. Therefore, the motion of the Hamiltonian system are the geodesics of this metric. And then it goes on, and well, then he has the singularities where the potential goes to minus infinity, because because we are assuming that the potential is Coulombic. Then what he needs to do is to regularize the flow on a neighborhood of these singularities. Then the flow becomes complete and compact. And then it goes on and proves that for sufficiently high energies, in fact, the Gaussian curvature is negative. And therefore, it gets a geodesic flow on a surface with negative curvature, and therefore Anosov. The other properties are consequences. Okay. Now, with magnetic field, I've studied with Robert McKay previously the case of two particles interacting under the action of a uniform magnetic field which is orthogonal to the plane of motion. Basically, this is a two-body problem, but with all the complexity, or some of the complexity, of the free-body problem. Since each particle feels each other, and each particle, in some sense, feels some Lorentz force which makes it rotate. So each particle feels two forces acting on it, which is the same thing as happens in the free body problem. So for this problem, we assume that the interaction potential has rotational symmetry, and this provides us with free conserved quantities, plus the Hamiltonian. So this is a 4-degree of freedom, and we have 4 independent first integrals. But we prove that the system is not integrable. What happens is that the integrals do not commute, and therefore you cannot obtain integrability. Okay, so let's say that the charges have, that the particles have charges E1, M1, E2, M2. Okay, as before, fix E1, choose units such that E1 is equal to M1 is equal to 1. And what we prove is the following. So this is the axis for the second charge. This is the axis for the mass of the second particle. And what we can do, we can use symplectic reduction to prove that the system that we can use the integrals of motion which are known, 2 linear motions and 1 angular motion, to reduce the system to 2 degrees of freedom. But we can prove more. We can prove that if E1 over M1 is equal to E2 over M2, then there exists another conserved quantity, and in fact the system is integrable in this region of parameter space. Nearby, you see what you usually see in KEM. So some tori persist and some others break up. So in here we have periodic and quasi-periodic motion, and in here we have this standard KEM theory result. So this is in the case where the charges have both positive signs, or have the same sign, so the repulsive motion. If the charges have opposite signs, then we can prove the following. Except for one line, where E1 over M1 is equal to -1, except for that line, we can prove that the system always contains a set, an invariant set with positive entropy, which is a suspension of a subscript of finite type. So we prove that the system is non-integrable here. Moreover, we prove that the motion of the two particles is always bounded, except for a region of perimeter space where E1 plus E2 is equal to 0. This is the very special case of the hydrogen atom. The two particles have the same signs, but opposite signs. Okay. Then we moved on to look at the motion of these two charges interacting in space. Okay, so this was a first step. In space, we have now a 6 degree of freedom Hamiltonian system and only 4 conserved quantities: free linear momentum and 1 angular momentum. Again, they don't commute. And the best we can do using this symplectic reduction thing is to reduce the system to 3 degree of freedom. In the same regime of parameters, here, when the ratio of charges to masses are equal, we have these extra conserved quantities, so 2 degrees of freedom, and there's an invariant subspace of the phase space where the two particles are in fact in the same plane. In this case, they reduce to the planar case, and the particles do all the dynamics of two-dimensional case when moving in the same plane. Okay, so then after that we look at the problem of studying the scattering map associated with this problem. So basically, what we do is that we shoot two particles in opposite directions and see how they interact. When they are very far apart, they move in helices. When they approach each other, they start interacting. So then we prove the following, that for rational independent gyro frequencies is just this, is proportional to this ratio of charge to mass. Then we can use averaging, and the magnetic moments, that is the radius of the helices, are preserved. So what happens is then when they approach, they interact, they sort of rotate the centers of their helices, and they keep going. If there are resonances, then there may be a change, an exchange of energy between the two particles. So when they interact, they not only they rotate their centers, but there's also a change in the radius of the helices. Okay, more. We have identified 4 special types of dynamics in this case. If the particles have opposite charges, you can have a bounded dynamics. It's something like a molecule-like dynamics. And you can have some kind of dynamics where they come, they interact, and they go away. In the case where the charges have the same sign and thus repulsive motion, then if the energy is sufficiently large, they can come, interact, and go away, or they can bounce back due to the repulsive nature of the potential. Okay, so there are a lot more stuff done in this kind of problems. For instance, these twisted geodesic flows or magnetic flows, and there are a lot of works by Arnold, Paternine, Bialy, Contreras, Maccarini, Mary. There are n-body problems on constant surface of constant curvature by Diaco. I guess Chancine is also working on that. There are these works about choreographic solutions for n-body problems. So my goal is to look at this problem as a first step towards looking at the problems of two interacting particles on curved surfaces. So one of them is fixed at the moment. Okay, so we will assume that all the particles on the lattice have unitary values of charge and energy, charge and mass, and that the moving particle has some positive mass and non-zero charge E. So the magnetic field is uniform and orthogonal to the lattice, to the plane where the lattice is. We could have this electric field inside the plane of the lattice, but let's keep it zero for the moment. There's no gravitational effects and everything is classical. Okay? So, as a first step to formulating the problem, just let us just look at the dynamics of one charged particle in R2. So you have this mass, the non-zero charge, and the magnetic fields. You can write down the Lorentz force in that form, where J is just the standard symplectic matrix of R2. So that is basically the exterior product between V and B. V is the velocity of the particle. Then you can write down this as a system of first-order differential equations and introduce some conjugate momentum, P equals to mv. So the standard momentum, mass times velocity. Oh, you end up with an Hamiltonian system with a Hamiltonian function which is only kinetic energy and non-canonical symplectic form. So your Lorentz force, instead of showing up on the Hamiltonian, shows up on the extra term you see here on the symplectic form. Another way around this is to introduce different coordinates. So you introduce a vector potential, and in this way your Hamiltonian function has non-standard kinetic energy, but you can choose this vector potential A in such a way that this term goes to 0, and you recover your standard canonical Hamiltonian equations. Okay, so the dynamics of this system are trivial. The particle just goes around as a fixed center called the guiding center, fixed radius, and note here, the radius is the quotient between energy, this size of the momentum, and the magnetic field B, the intensity of the magnetic field B. And the particle goes around with fixed frequency, which is usually called gyro frequency. Okay, the motion is clockwise if the charge is positive sign, and anti-clockwise otherwise. So, Knauf has already proved that with no magnetic field, the system is Anosov for sufficiently high energies. So, this has to do, so if the magnetic field is small enough, then this is just a perturbation of Knauf's work, so it's still Anosov. So we look to ranges of energy where the ratio of energy to the intensity of the magnetic field is small enough. So smaller energies or larger intensities of magnetic field. So this is no longer a perturbation. In fact, you start seeing elliptic behavior for given choices of energy. So the system is no longer Anosov. Okay, even if it's Anosov in the limit of very large energies or very small magnetic fields. Okay, so now what we do is we introduce this interaction potential, V. So the particle, so we can keep any kind of coordinates, the ones which make the symplectic form canonical, or the one which does not. And I'll use this notation. K just represents E times B. So think of K as some parameter controlling the size of the Lorentz force acting on the particle. So now V is the interaction potential between the moving particle in the lattice and the fixed charges. So we write this as a sum of potentials which are of Coulomb type near the lattice points. So this Rij is just the distance between the position of the moving particle and the point in the lattice Ij. And then we add this term here. This is generally referred to as a screening term. So this makes, in some sense, as a first approximation, you only look to the interaction of the charge, the moving charge, with the points of the lattice which are inside a small box, because it decreases exponentially. Okay, so these are famous potentials, are either screened Coulomb potentials, Ikawa potentials, or Debye-Huckel potentials. Okay, so now let's look at what do these potentials look like. So this is the picture for that potential when the moving charge has positive charge, and therefore the interaction between the charge and the fixed particles in the lattice is repulsive. So you can identify two critical level sets for the energy. First, H0, which is the minimum on each cell of the lattice of Vxy. And this is strictly less than H1, which is the minimum of Vx0 when x is between 0 and 1. Okay? So it's above H1, above H0, you start having dynamics, and the other critical point is above H1. So if your energy E is between H0 and H1, and you have your lattice, your particle is confined to regions on each cell. So you cannot move from one cell to the other. If your energy is above H1, then your particle is able to move in the lattice from one cell to the other, but the motion is always bounded away from the singularities. So in fact, you don't have any kind of collisions, as you would expect. Okay. So in the first case, in this case, typically your dynamics will be regular. That means periodic or quasi-periodic. While in this case, you have all the tools to have chaotic dynamics. I mean, by chaotic, I always mean positive topological entropy and diffusive behavior. Okay, but not Anosov, as long as I know not Anosov. Okay, so these are just some examples of this picture. So this is the case where the energy is small, like this. So this is just a cell, and you see some kind of quasi-periodic behavior there. And this is the case where the energy is already larger than H1, and you start seeing some drifting around of the particle. Okay? In the case where the charge is negative and you have an attractive interaction, then what you do is the following. So again, you identify the level sets, the thresholds in the energy where your behavior or the behavior of the dynamic changes. At least the projection of the level sets on the energy level sets on the configuration space changes its topology. Okay, so let's now define H1 as being the maximum of Vxy on a given cell, well, the supremum, the maximum, on a given cell of R2 over Z2, and this larger than H0, which is the maximum where x is between 0 and 1 of Vx0. Okay? Now, if the energy E is smaller than H0, what you have is the following. You have your lattice, and you'll see that the particles are confined to neighborhoods of the singular points. So what really happens here is that the motion is bounded, but the particles make some kind of crazy dynamics, always going into collisions or quasi-collisions with the singular points in the lattice. If the energy is between H0 and H1, then you start being able to drift around. So basically, everything is accessible in the configuration space, except for small neighborhoods of this in the center of the cells. So the particle can have collisions around, but it never goes to the interior, to the center of the cell. And if the energy is smaller than H1, all the lattice, except for the singular points, is accessible to the moving particle. So, in the proof for the existence of a suspension of a subshift of finite type, I'll focus on this regime. Okay. Okay. So this is basically what I was just saying. If the energy is small, you have some kind of crazy periodic or quasi-periodic dynamics. If the energy is between H0 and H1, you might have chaotic dynamics and you might have some diffusive behavior. And if the energy is large enough, then I'll prove that such chaotic orbits exist. Okay, so this is again some simulations showing the typical dynamics. So this is the dynamics on the small energy sets. The particle just goes through lots and lots of collisions, but the motion remains bounded. This is the case where the energy is higher, so that you can go from one cell in the lattice to the other, but without being able to access the center of the lattice. And this is the case of higher energies, where you can reach every lattice in every cell or every point in each cell of the lattice. Okay, so I'll focus my attention on this case. Okay, so the proof for the existence of chaotic motion is follows some ideas or the technique developed by Balatin and Robert Mackay in 2000. So they've proved the existence of this, they use a variational method to prove that if they are able to build a sequence of collision orbits or a chain of collision orbits, then they prove that the existence of this subshift of the suspension of a subshift of a finite type in some energy level sets. So they do this for the n-center problem. So they have n fixed centers, and they don't have any magnetic field. So I extend this result to being able to have these fixed centers in the lattice and correcting the potential in order to allow for the magnetic field terms in the Hamiltonian function. Okay. So I'll go briefly through this result, and then I'll do the other ingredients. So I'll prove that there exists this sequence of quasi-collision orbits. Okay, so let's focus on the configuration space. Q is R2, and S, let's take it at this lattice Z2. So we'll look at Hamiltonian systems on the cotangent bundle of this Q, R2, except for the lattice. So we'll go and remove the singular points. And we assume that these Hamiltonian systems have canonical symplectic form and are of this form. Some H plus some delta V. This V is just some interaction potential. So we'll look at the dynamics of these Hamiltonian systems as some perturbed dynamics of some original Hamiltonian system plus this interaction thing. Okay, so now this H is of this form. Some kinetic energy plus some potential, which may depend both on the position and the momentum. And now we need this to have the form which enable us to use our Hamiltonian with the magnetic field. So the potential needs to be some of this form. Okay, some potential which depends only on the position times some potential which depends on something which resembles a lot the angular momentum of the particle. Okay, and we assume that all of these functions are C4. V is the interaction potential. So in the neighborhood of a point of the lattice, it behaves like a Coulombic potential. And we assume that this is negative on a neighborhood of each point of the lattice. That is, the interaction is attractive. Okay? Now, we fix the energy large enough so that this set D contains more than one points in the lattice, so that we can be able to build these collision trajectories. And now we'll look at the Hamiltonian system H delta on each level set E of this form, satisfying this property, as a perturbation of the Hamiltonian system H naught. Okay. So now we suppose that this Hamiltonian system H naught has non-degenerate collision trajectories. By that I mean trajectories of H naught which connect points in the lattice in some time tau k, and are such that you don't return to the same point. Okay, I don't want to return to the same point because, and it will be clear in just a moment, I want the particle to be able to change direction when it goes through a collision. So let me go back to the lattice. I want to have trajectories of H naught, and H naught is the Hamiltonian without interaction potential. So as I told you, these are just circles or arcs of circles. So I want to join particles in the lattice by arcs of circles, okay? And at each point, I will want to change my direction. So I have this tangent. I want to leave to some other lattice point without changing the direction. I'll tell you just in a moment why I need this condition. Okay, so, and moreover, we don't want to go through any other point in the lattice, and this time from 0 to tau k. Otherwise, we will choose a smaller time, and it will be done. Okay, by non-degenerate, we mean that the trajectories gamma k are non-degenerate critical points of the action in phase space, constrained to level sets of energy E, and fixed boundary conditions Q0 and Qt for some time t. Okay, now we call a chain to a sequence of collision orbits such that each element in this sequence has the initial point where the previous element in the sequence had the final point. And this direction change that I was referring there holds. And now the concept of shadowing trajectory. For each k on a set k, finite set k, you take wk to be a neighborhood of these collision trajectories gamma k. We say that the trajectory gamma shadows this chain, this sequence of collision trajectories, if there exists an increasing sequence of time ti such that the trajectory, the shadowing trajectory gamma, is inside the neighborhoods of these collision trajectories. Okay, so the theorem is the following. Now, given a finite set of non-degenerate collision orbits, there exists some positive constant epsilon naught, such that for all delta, delta is the parameter controlling the size of the interaction potential, such that for all small enough delta and any chain gamma ki that you can build, then there exists a trajectory gamma from R to ds, d except the lattice points, of energy E for the system H delta, which shadows the chain gamma ki. And moreover, such trajectory is unique up to a time shift if we take the neighborhoods of the collision trajectories small enough. This orbit gamma converges to the chain of collision trajectories if you make the delta controlling the size of your interaction potential small enough. And this orbit gamma avoids collisions by a distance of order delta. This is why I need the change in direction condition. If I don't make the particles, the collision trajectories change conditions, so if if I arrive with a collision with a given direction and I leave on some with the same direction, then this last statement doesn't hold. So I need the change of directions to have this bound away from a collision. And the reason is the following. So so this is some sort of an anti-integrable construction. So you have these collisions. Let me just focus on one point. You have some collision trajectory arriving at a point, something like this, and you have one going away. So what you do is the following. You regularize some kind of Levi-Civita regularization. And basically, this trajectory is in a stable manifold. So the singularity becomes an hyperbolic fixed point for the regularized system, and the trajectories arriving are in the stable manifold for this hyperbolic system. The collections leaving are on the unstable manifold, and when you perturb, you see, we are assuming that these trajectories are non-degenerate critical points of the action. So then you use an implicit function argument, and you get the orbit for positive small delta shadowing that trajectory. Okay, so this change of direction condition is used here so that you don't go arbitrarily close, so that the shadowing orbit doesn't go arbitrarily close for when you perturb the continuation of your trajectories, it doesn't go arbitrarily close a lattice point. So you need change of conditions, change of directions to ensure that. So basically, if you build a sufficiently large set of collision trajectories, then a consequence of this theorem is that there exists an invariant set in some energy level set, H delta equals to E, which contains a suspension of a subshift of finite type. So if you have enough energies, then you can estimate the topological entropy of this subshift and ensure positive topological entropy. Okay, So now we need to ensure that for our system, so having extended that result, we need to ensure that our system has enough collision trajectories. So the theorem is the following. So you assume that the charge of the moving particle is negative. And now for every value of the energy h which is large enough, it doesn't need to be very large, but it needs to be at least that value. Then you have at least 8 non-degenerate collision orbits leaving from one point to other point in the lattice. And the number of such collision orbits grows with the energy, as you would expect. Therefore, using the previous theorem, what we obtain is that for every finite set k of collision orbits, there exists some constant such that for every chain gamma ki that you build up such collision orbits and every small enough parameter delta, then you have a unique trajectory of energy h near the collision chain and converging to the chain as delta goes to 0. Now, you may already be seeing what's the strategy. So we go back to the lattice, okay? And let's assume that the particle leaves from this one. So these 8, let me tell you, are just, it's this 8 that we get are basically the ones connecting to the nearest neighbors. Okay? As h grows, you can estimate the number, the increase in the size of orbits. So all we need to do is go back to our unperturbed zero interaction potential and rewrite it in this form. So this is our W, the potential without interaction. And we need to find trajectories connecting 2 points in the lattice for some time t for fixed energy E. Okay, we can take the initial point to be the origin due to Z2 invariance of the system, and we can solve this system, and this is linear. Okay. Alternatively, if you prefer, you can also use this one and in the non-canonical coordinates. Okay, so the motion is pretty simple. It's just circles around the guiding center with a fixed radius and fixed angular velocity. So you can write down explicit forms for these trajectories. And then what you need to do is to fix the initial conditions, fix the final conditions, fix the energy, and solve everything with respect to your parameters. And your time t must be in this interval. Otherwise, you would return to your initial point without having any collision. So it's a pretty simple exercise to solve this system. And what you get is a condition of this form. Now, for the solution to be well defined, you need this function to be always larger than 1. Otherwise, this cosinus of phi and sinus of phi would be larger than 1. So if this thing is larger than 1, you get your desired condition on the energy. So for that, if the energy is larger than net bound, you get a large enough set of collision orbits, and then you can apply the other theorem and shadow these collisions of this set of collisions of the set of collision trajectories. Okay, so the next steps are the following: to try to generalize this procedure for the lattice with positive charges. Okay. So if we have positive charges, then we can still use the collision trajectories connecting 2 distinct points in the lattice, but we cannot go straight to collisions. What happens is that we need to provide the following argument. So we use trajectories which connect, well, you make the interaction potential 0 outside these balls around the lattice, and you use the collision trajectories to connect these neighborhoods of the points of the lattice. Inside each point in the lattice, inside each neighborhood of a point in the lattice, you use the interaction between your particle and the single point in the lattice. And this will provide you some trajectory of this kind. And then you use, again, some collision trajectory going to the next neighborhood. So now you need to use the same kind of arguments and use non-degenerity to prove the existence of a shadowing trajectory. So I'm working on this at the moment. The other steps would be to move to three-dimensional lattices. Instead of having just the standard lattice, you have several ones. It's harder to construct the trajectories, but it's feasible. Okay? So I guess this is all. Thank you for listening. Thank you for coming. Congratulations, Maurício.